All right, welcome everyone. So it's my pleasure to introduce today as the AI speaker, Daniel Fremont, who is a PhD student at UC Berkeley, working in the group in logic and the methodology of science with Sanjit Saikia. He received a BS degree in mathematics and physics from MIT in 2013, and his research is generally in reasoning to with algorithmic improvisation. So welcome again, Daniel.
Thank you, Satish. Hi, everyone. Thank you for inviting me to speak today. So, as the title says, I'm going to be talking about approaches to safe autonomy via this framework called Algorithmic Improvisation, which we've been working on for a few years at Berkeley. So the context for this work is the rise in recent years of autonomous systems being used in safety-critical applications. So a classic example is self-driving car. Also drones, people have been hearing a lot about, but even things like industrial robots, increasingly personal robots, or something like a smart grid is expected to operate with less and less human supervision, and in a context where an error by the system could have catastrophic consequences. So as a result, these systems really need a rigorous design process that could give you strong guarantees about their reliability. But it's difficult to do that. So we have seen incidents like this one where the system behaves in a way that maybe we did not expect. So this is a particularly interesting one involving an Uber self-driving car. This green car on the left, a human turned left even though they couldn't see each other and they got in an accident. So this is an interesting case because actually maybe the Uber didn't do anything particularly wrong, although perhaps it should not have gone at 40 miles an hour through an intersection that it couldn't see where anyone was coming from. But there was an interaction between a human driver and the self-driving car here that led to this accident. So what you'd like to do maybe is understand why did this accident happen? How could the system be changed so that it didn't happen? But there aren't really tools for doing that kind of analysis. This simulation is produced by one of the tools I'll talk about in this talk. It's one of the first things that lets you do that type of analysis.
Just a question.
Yeah.
Ubers, they don't have 360.
So the problem here was that because of these two lanes of stop traffic, neither car could see each other.
But I'm just looking at the view from the drivers, like.
Oh yeah, this is just what a camera is showing from the front of the car.
Right, but they have more
give you an idea.
cameras.
Yes, of course, and they have LiDAR and all those things. Right, but
Those
neither.
cameras also.
Yeah, because they would have to look through these.
No, I understand, but once it's already like.
Oh yeah, like immediately before.
Like right now, already see them.
Right. But then it was too late to take any action at that point. That's right.
Machine reacts more swiftly.
Right, but I think so this is kind of slowed down, but the car was moving at 40 miles an hour. So I think there was no way at that point the accident could have been avoided. Okay. So the open question really is how can we build safe autonomous systems? And there's a lot of interest in this question because of the imminent deployment of systems like self-driving cars. And there's a lot of research going on about this question. For example, the DARPA Assured Autonomy program, which we're working on, is adjacent to this project. But I think it's still safe to say that this is an open question. And why is that so difficult to build these systems in a reliable way? I think there are really three different aspects that contribute to this. One is something that we're familiar with in software engineering for a long time now, it's just the complexity. So even an ordinary car, not a self-driving car these days, can have up to 150 million lines of code in the computers inside it. So no individual person can keep track of the full complexity of that system. Furthermore, with something like a self-driving car, the computer has now physical agency. It's interacting in the physical world with this very complex environment that contains other agents like human beings moving around that you can't predict what they're going to do ahead of time. And finally, in response to that very complicated environment, these systems increasingly are using machine learning to understand and interpret that environment. But those models, in turn, are extremely large, potentially some massive convolutional neural network, for example, and it's difficult for even a designer to understand what it's doing because it was essentially designed by an algorithm, optimization algorithm. So as a result of all of these, even the designers of a system increasingly cannot really understand how it works in any detail, and in particular, how it can fail. So the approach that I've been taking to tackle at least the technical side of this issue uses formal methods. So formal methods is a field of computer science that uses rigorous techniques to design, model, and analyze systems based on formal mathematical reasoning. So the kind of gold standard in formal methods is to prove formal, rigorous guarantees about a system. Like it's guaranteed under certain conditions to operate correctly. But as I'll try to argue in this talk, even for systems that are extremely complicated or black box, maybe there's neural networks involved and it's difficult to prove ironclad guarantees about it, formal methods can still help you by allowing you to do principled, intelligent forms of testing. So let me make this a little bit more concrete and tell you about some ways that formal methods can help in the design and analysis of an autonomous system. So, and in particular, some approaches to that I've worked on myself. So if you have a system like a drone or a self-driving car, what's going on inside that system? You have sensors that are giving you some information about the environment. You may have communication happening between your system and other autonomous systems or to infrastructure or something like that. And then in the computer, you might be doing machine learning to perceive the world and interpret this information you're getting from the sensors. On top of that, you might be doing probabilistic inference to reason about what is the most likely state of the world, what is the most likely action that this human being I'm observing will take next. And on top of that, you're doing some kind of planning. And this usually has to be reactive planning because the environment contains agents like people that you can't predict what they're going to do. So formal methods can help with the development of all of these different components. So for high-level planning, for example, you can use synthesis to generate a correct by construction controller. And in particular, in this talk, I'll talk about how to do that for systems where you need randomized behavior. For probabilistic inference, you can use algorithms I've worked on for model counting to get strong guarantees on the results of the inference that are stronger than you would get from, say, MCMC type algorithm. If you have communication, you might be worried about privacy issues. Maybe even if you're encrypting the traffic pattern or the way your protocol works might leak some information about where the cars are or how some other secret information that's part of your system. And you can use techniques based on constraint solving to compute bounds on how much information can be extracted from that interaction. If you want to test your machine learning system, you might want to generate random environments. And there's also techniques I've worked on using constraint solving, again, to generate random solutions to constraints that you can use for that. And related to that, you can use that for human modeling, generate random human-like behavior. And I've mentioned a bunch of these things rely on constraint solving technology, so I've also done some work on just trying to understand why SAT solvers work well in practice and when they do or do not. So in this talk, I'm going to focus on these particular applications, and especially on a recent project that we've been working on to create a domain-specific language to describe and model the environments of these kind of systems to do various design and analysis tasks. And I'm going to talk about these three particular applications because they're all instances of what you might call constrained random generation. So for example, if you want to synthesize a controller for a robot that's exploring some unknown environment, you want to generate trajectories for the robot that are safe, they don't collide with obstacles and things like that, but you might want to introduce randomness so that they cover this unknown space in an unbiased way. Similarly, if you want to do human modeling, you would like to generate human-like behaviors, and those inherently have to have some randomness in them to realistically model the stochasticity of human behavior. And finally, if you're doing simulations to generate training or testing data for some machine learning system, you need a certain amount of diversity in your test and training set so that you don't overfit, but you'd like to be able to tune what type of data you get, and you can use constraints for that again. So underlying all three of these applications is this project we've been working on called Algorithmic Improvisation, which is really a way to generate random solutions to constraints with a certain amount of diversity. Okay, so let me motivate a little bit more why you need randomness. So for example, let's say you want to generate a data generator for an object detecting neural network. It takes images like this one and puts bounding boxes around all the cars, say. So the task could be generate images of bumper-to-bumper traffic. That's obviously a huge space of images. These are three very different images, all of which could reasonably be described as bumper-to-bumper traffic. And randomness lets you cover that space evenly. Another application of randomness is realism. So let's say you want to design a lighting controller for your house that makes it look like you're still at home when you're on vacation. So it turns the lights on and off in different rooms. if you learned a deterministic model of how you use the lights in your house, that would obviously be unrealistic because some days you wake up a little bit later, some days you cook or do not, and so forth. So here what I'm showing is these 3 red lines at the top are actual power consumption traces over the course of a day from some human being in a house. And the rest are ones that we generated using algorithmic improvisation. And the final application of randomness is unpredictability. So if you want to do planning for a surveillance robot, say, you're patrolling a museum, you want to make sure you visit each important location sufficiently often, say, if you solve those constraints and you found one route and did that every night, it would be highly predictable. Someone might know every night at 2 a.m. you're on this end of the museum, so let's break into the other end. So you'd like to introduce randomness into the planning to make the robot's location harder to predict. And I'll get back to what this simulation is showing a little bit later.
And
Yeah.
so there's different kinds of randomness.
That's true, right.
So you're going to
In this talk, basically, I'm going to talk about almost the simplest thing you could imagine. And of course, we're interested in more sophisticated notions of randomness.
just uniformly at random.
Almost a slight generalization of that. We'll see in just a moment. Okay. So in all of these systems, randomness was really essential. So for the system to be operating correctly, it has to have randomness in its behavior. But at the same time, you don't want completely random behavior. You have formal specifications that the systems need to satisfy. So in this lighting control example, you might want to say, don't use more than a certain amount of power. If you're generating images to test a network, you want realistic images. So you don't want images, for example, where 2 cars are intersecting each other. And finally, if you're doing robotic planning, you have safety constraints, like don't collide with another drone that's moving around in the same workspace. So really, the question is, how can you design a system which has both random behavior, but is still controlled? It satisfies formal requirements. And that is what algorithmic improvisation is about. It's a framework for automatically synthesizing systems, which could be reactive, that have random behavior, but still give you formal guarantees. And there are really 2 types of guarantees. There's the usual type of guarantee from correct by construction synthesis, which is a guaranteed safety. You can specify some safety properties, and we ensure that those are always satisfied. The new type of requirement is a randomness guarantee, that no matter what sort of environment the system operates in, its behavior will have a certain amount of diversity. And that's what really makes this a new type of problem. Randomness is part of the specification. And that will, as we'll see, require us to use different techniques than what people have looked at already in reactive synthesis and just uniform sampling, for example. But we argue that it is still a core problem in CS, useful for a bunch of different applications and drawing on ideas from several different areas. For example, from formal methods, we're using different notions of specifications, and some of our algorithms use SAT solvers internally. From automata CS theory, we're using some algorithms and theory about automata, and also, of course, randomized algorithms, because the implementations that we want to generate are inherently randomized. And finally, from programming languages, as we'll see in the last part of my talk, we're using probabilistic programming languages as a way to specify kinds of constraints that you want the system to satisfy. Okay, so the outline for the rest of the talk is I'm going to start by defining the kind of core computational problem in algorithmic improvisation, which we call control improvisation, and I'll motivate the definition a little bit with some applications. Then I'll tell you a little bit about the theory of the problem, in particular some efficient algorithms we've given for various cases and hardness results for other cases. And then I'll go into some detail on one of the recent applications we've been looking at, in particular designing and analyzing perception systems. And then I'll close with some prospects for future work. Okay, so to start with control improvisation. So here's an experiment, kind of a motivating example that we did of a surveillance drone. This is being played back at high speed. The drone has kind of a home base, that large piece of paper on the left, and it's supposed to visit these 5 other locations. But we've said that the battery life isn't long enough to visit all of them at once, so it has to periodically go back to recharge. And you'd like to do this, as I said before, in a kind of random way so that it's not predictable what order you'll visit these different locations in. And so here what's happening is we're using one of the algorithms that I'm going to talk about later to do the high-level planning. That's going into a lower-level planner, which actually reasons about the dynamics of the drone, and then that's being turned into control actions of the drone here. So how would we formalize this kind of robotic surveillance problem? So we want to patrol an area in an unpredictable way, say. What are some requirements that we might have? So obviously, we want to visit each of various locations sufficiently often. Yeah?
A small question. Does the drone has its own camera and it's like following the path, or does it have access to the like high level.
Right. In the experiment I just showed, there was a Vicon kind of system.
Yeah,
So we
it-
have
it
global
does
information.
see, like goals.
Right. That's right. So everything I'm going to talk about in this talk, actually, we're assuming kind of perfect information.
Okay.
It's interesting to generalize the problem to partial information things, but we have not really done that yet. So that's one type of requirement you might have. Another requirement might be an efficiency one. So one way you could make the route arbitrarily random is by adding in all kinds of wiggles everywhere, but then it might be an extremely long route. So you might want to say that the route should usually be close in length to the shortest possible route, say. And finally, of course, we don't always want you to take the same route. So notice that these are three very different types of constraints. The first is what I'll call a hard constraint. This is something that has to be true of everything you generate. The second is a soft constraint. It only has to be true some of the time. And finally, the last is actually a property of the distribution of behaviors of this system, and it says that it has to be kind of not too concentrated on any particular behavior. And we see these same types of constraints in other applications as well. So for instance, we're generating traffic images. We have realism requirements like objects should not intersect. We also would like to say this image should somehow usually be similar to real-world traffic so that it's useful for training and testing purposes. And of course, we want to generate a diverse set of images. So again, we have these three different types of constraints. And we see these in other applications as well. For example, music improvisation, which is actually where the name of this problem comes from. That was the first application we looked at, trying to generate variations on some melody subject to constraints about the genre. But also software fuzz testing, you're generating random files subject to constraints, a bunch of other applications. In all of these, you're trying to generate sequences of actions for the robot or symbols for a file subject to these three types of constraints. Every sequence has to satisfy a hard constraint. Most sequences have to satisfy the soft constraint, and you have a randomness requirement saying that nothing is generated too frequently. And control improvisation is just a precisely defined theoretical problem that captures these kind of requirements. And as I hinted at before, the reason we defined a new problem is that there are a bunch of related problems that get at different aspects of this, but not all of them at the same time. For example, there have been work in computer music improvisation on factor oracles and in fuzz testing on mutational fuzz testing, where you can generate kind of random variations on things, but you can't impose a kind of global hard constraint. In the other direction, there's work on uniform sampling from constraints, like some of the work I've done, and also work on a generative fuzz testing where you can enforce a global constraint, but you don't have a way to naturally put in these soft constraints. And then along a different axis, there's been lots of work on reactive synthesis where you can ensure that some specification is satisfied even in the presence of an unknown environment. But those algorithms don't allow you to do it in a random way. You might just end up with a completely deterministic policy. And control improvisation combines all four of these aspects. Okay, so now let me actually try to define it formally for you. There are a few components to the definition which I'll illustrate using this robotic surveillance application. So let's say we want to generate sequences of some length n, which I'll just say is fixed at one particular length. We can handle a range of lengths. The important point is that it's bounded. It's part of the problem definition. Length n from a finite alphabet sigma. So for this drone moving around in a grid world, say it could be the four actions: move north, south, east, or west. And our hard constraint will be given by a specification h. So by specification, I mean any formalism that can define a property. So it could be a Boolean formula, an automaton. The complexity of the problem will vary depending on what representation you're using. So here it could be our robot should visit all four of these locations, avoiding collisions with this other robot that's moving around in the same space. And our soft constraints will be given by another specification, S. For example, here it could be an efficiency thing, like don't redundantly visit one of the four circles. Okay, so once you've specified those properties, that defines a few sets. So if you think of this as being the space of all possible sequences of actions we could generate, that contains things that violate the hard constraint, like where the two robots collide, for example. So I'll call this set the improvisations. These are the strings that length n strings that satisfy the hard constraint. So this is things like this trajectory where you avoid collisions and you successfully visit all four locations. But that particular trajectory visits one of the circles twice, so it violates the soft constraint. And we'll say the admissible improvisations are those which satisfy both the hard and the soft constraint, like this trajectory, for example. So these sets I and A are what we need to give the formal definition. So here it is, given all those properties and some parameters epsilon, lambda, and rho, which I'll tell you about in just a second, a distribution on words is an improvising distribution if it satisfies three properties. The hard constraint says that if you generate a word from the distribution, you always get an improvisation. So you always satisfy this property H. The soft constraint is very similar. It says if you generate a word from D, you get something that's admissible, satisfies the soft constraint, with probability at least 1 minus epsilon. So epsilon here is controlling how tight this soft constraint is. And finally, the randomness requirement says that for everything you're allowed to generate, its probability has to be between lambda and rho. So if you want to make sure that nothing is generated too frequently, you can decrease rho. If you want to make sure for testing, for example, that everything is generated with at least some probability, you can increase lambda. So for this talk, just to simplify things, I'm going to take lambda equals 0 everywhere, but we have a more general theory that handles arbitrary lambda. So given all these parameters, that makes up a control improvisation instance. And we say the instance is feasible if one of these distributions exists. And in that case, what we want is an algorithm that samples from one of these distributions. We call that an improviser. So in this example, say, let's suppose there are only 3 admissible traces and 2 non-admissible improvisations. Of course, there are millions for that grid world example. But if it was just these 5, then if we put epsilon and rho equal to 1/4 and lambda equals 0, say, then here's an improvising distribution. Return each of these 3 with probability 1/4 each, and these 2 with probability 1/8 each. So then we would satisfy the hard constraint because we always get something in I. We satisfy the soft constraint because with probability 3/4, we get something in A, and epsilon, the error probability is 1/4. And we satisfy the randomness requirement because nothing is generated more than 1/4 of the time, and that's rho. Yeah.
So to compute those probabilities, you have to know about all past potential.
That's right. Yeah, so that's why this could potentially be a non-trivial problem if this space is exponentially large, for example. So I'll talk about just a bit later is when we can efficiently do it. Yeah. Okay, so that was the basic version of control improvisation where it was kind of static. You just generated the behavior all at once. If you have an adversary, like you don't know what this other robot is going to do ahead of time, then we have a reactive version of the problem. I won't define it fully formally, but just tell you how it differs from that previous definition. The most important thing is that now, instead of generating a trace all at once, you alternate with the adversary. So it's a 2-player game. You alternate picking actions to build up a combined trace. We still have the 3 types of requirements, but now they have to hold against every adversary simultaneously. So for example, no matter what the adversary does, we should never get a trace with probability greater than rho. And now the improviser becomes an improvising strategy. So it's a function of a probabilistic algorithm that takes in what the adversary has done so far and computes the next move. But once you do this, you get a way to do reactive synthesis in a randomized way, at least for bounded time. Those of you who are interested in reactive synthesis, you can ask me about infinite time later on. Even in the finite bounded case, it turns out to be quite non-trivial. So here's an example where the simulations I showed before are coming from. So the black line is showing a simulation of a drone moving using our improvisation algorithm with these specifications on the left. The dashed blue line is an adversary that I've had move in the exact same way in all 4 of these, just to show you that our improviser is doing something very different, even with identical adversary behaviors. The reason the lines are not beautiful and perfect, the lines of the grid world, is that, again, we're using control improvisation for the high-level planning on the grid world, and then a lower-level controller to actually reason about the dynamics. And that's what's being shown here. And one point to mention is that here, the randomness requirement we're using is to use actually the smallest row for which the problem is feasible, which is possible to satisfy the hard and soft constraint. So in that, some sense, that's the maximally randomized strategy. So our algorithm can also compute that for you. Okay, so that's what I want to say on the definition of the problem. Are there any questions at this point? Yeah.
So actually, this work, especially with adversary present, reminds me of like Millen Tambi's work with Tam DPs. Are you familiar at all with
right.
this?
Yeah. So I guess at least all the work that I know of using POMDPs, there isn't a way to specify, kind of enforce a certain amount of randomness on the policy that you would learn, right? So the usual thing is you have...
It's inherently probabilistic.
Yeah, right. The dynamics are probabilistic, right? But the policy that you might learn could be deterministic, right? So the difference here is kind of our dynamics are deterministic, but we want you to introduce randomness. Okay. So let me tell you a little bit about the theory of the problem. The most basic question is, when is it even possible to solve one of these? Let's not worry about the complexity. When does one of the distributions satisfying those three requirements even exist? So with lambda equals 0, which is what I'm going to talk about, it just requires these two sets I and A to be large enough. So here's the particular condition. It's actually pretty easy to see that these are necessary requirements. So for example, suppose you had fewer than 1 over rho improvisations. Then even if you gave them all the maximum probability you're allowed to rho, it wouldn't add up to 1. So you need to have at least 1 over rho of those. Similarly for the admissible improvisations. And you can actually see that these are, with a little more work, they're sufficient as well. So let me just go through that just to give you an idea. So suppose one of those distributions exists. If we actually assigned rho to everything in I, then that's at least as much as what the actual distribution D assigns, because it can't assign more than rho. But that, by the hard constraint, I mean, that's just this probability, which by the hard constraint has to be 1. So rearranging this, you get there have to be at least 1 over rho improvisations. Very analogously, if you assign rho to everything in A, that's at least the probability that D assigns to it, which is this probability. And by the soft constraint, that has to be at least 1 minus epsilon. So you have to have sufficiently many admissible improvisations. So that shows that these are necessary. For sufficiency, the core idea is to look at this quantity. So where does this come from? The idea is you first try to assign the maximum probability you can to everything in A, the admissible improvisations. Now that might end up putting more than rho on them, in which case you clamp it at rho, and the extra probability you have to put on the other improvisations, the things that aren't in A. So this is kind of the optimal error probability. It's the smallest error probability that you can possibly do. And then the idea for the distribution is just pick uniformly from the non-admissible improvisations with this probability. Otherwise, pick uniformly from the admissible improvisations. And this clearly satisfies the hard constraint because you always get something in the set I. And the soft and randomness constraints, you just need a little case analysis for which of these two you're in, but it's pretty easy to see that it works. So this is a pretty simple construction of an improvising distribution. And we can do the, and so what we want, of course, is not just a single improvising distribution, but a general algorithm that can go from an instance of the problem to an improviser. That's like a synthesis algorithm, taking the specifications and giving you an implementation. So we call that an improvisation scheme. And in particular, we'd like an efficient one. So we say a polynomial time improvisation scheme for a class of instances is an algorithm that, given an instance in the class, returns an improviser if the problem is feasible, if an improviser actually exists, and otherwise returns some symbol saying it's impossible. And furthermore, the algorithm and the improvisers it generate have to run in expected polynomial time in the size of the original instance. So both generating the implementation and the implementation itself are polynomial time. So the construction that I gave before actually gives us one of these whenever we can implement a few basic operations on specification. So if you can efficiently intersect and take the difference of two specifications, restrict one to a given length, and then more interestingly, count the number of words satisfying a specification and uniformly sample from those words. Now this might be highly non-trivial, so like as Christina mentioned, if you have only an implicit description of these sets, like the specifications are Boolean formulas, then counting and uniformly sampling are very non-trivial. You have to use some algorithm like the work I've done on model counting to do that. But if you can do all of these things, then there's an improvisation scheme. And in particular, if you can do these in polynomial time, then there's a polynomial time improvisation scheme. And the way it works is pretty straightforward. Using these first three operations, we construct specifications for all of the sets that we care about. The improvisations, the admissible ones, and the non-admissible ones. We count them using this, and we check the inequalities that we had looked at in the theorem before. If they're violated, you return impossible. Otherwise, you sample uniformly from either the admissible or the non-admissible improvisations with the right probabilities, basically that epsilon opt that I showed you before. And this gives you an improvising distribution. So when we can implement this, we get an efficient algorithm. And we can do that in some important cases. So in particular, for deterministic finite automata, there are classical techniques for counting and sampling. So that's actually what was being used in the drone example that I showed before. We encoded those specifications into an automaton and used this algorithm. Another interesting case is unambiguous context-free grammars. So if you're doing fuzz testing, for example, You might use a grammar to describe a file format that you want to generate inputs from, and then you can also do this efficiently. So the picture we get looks like this. If this is the type of the hard specification and the soft specification. For deterministic automata and unambiguous grammars, it's polynomial time. For general grammars or non-deterministic automata, it becomes equivalent to this difficult counting class of problems, sharp P. Interestingly, that also happens if you have two unambiguous grammars. We have to show a little complexity result for that. So you can ask me later if you're interested. We also have approximate algorithms for Boolean formulas based on SAT solvers. So we can't solve the problem exactly, but we can approximate it. So that was all for the non-reactive case. For the reactive case, things are pretty similar. Again, feasibility, which is here like realizability in reactive synthesis, reduces to counting. So now there have to be sufficiently many ways to win the two-player game. So you can imagine, like in ordinary reactive synthesis, you just need a winning strategy. Here, if there was only one way to win, like the adversary could force you to take only one sequence of choices in order to remain safe, then you couldn't win in a random way. So the result that we get actually looks very similar to what we had before, except now we're using this new notion of the size of the sets I and A, which we call width. So the idea of width is it counts the number of winning plays minimized over all adversaries. So the adversary tries to force you to choose from as few safe options as possible. So here's the formal definition. I'll just go through it. Here, sigma is running over our choice of strategy, the improviser's choice. Tau is the adversary's strategy. And by P sigma tau, I just mean the probability of getting a particular trace W given those two strategies. So this term is just counting how many traces in the set X have non-zero probability. How many of those traces can actually happen. And then we minimize that. The adversary tries to minimize it, and we try to maximize it. So it turns out that although the conditions for feasibility look a lot like the non-reactive case, actually constructing an improviser is far more complicated. I won't get into the details, but just one thing that kind of indicates this is that even for something like a reachability game, if you're familiar with reactive synthesis, for reachability and safety games, it's always possible to win by a memoryless strategy. But that's not true here. Even for those types of games, in order to win in a random way that satisfies the hard, soft, and randomness constraints, you need to have memory in some cases. So our strategy does a kind of random walk, but with a little bit of memory. So just to give you a vague idea, here's an unrolling of one possible game where we're trying to get to these winning states and not go off to some losing state. So like here, the width is 4, because it turns out there are 4 ways there are always at least 4 ways we can win from that position. And so basically we do kind of a random walk weighted by these. So from this position, we go here with 1/4, here with 2/4, and here with 1/4 probability. That's the basic idea, and then we have to have some memory on top of that. And we can compute these widths by dynamic programming efficiently in some cases. So in particular, again, for deterministic finite automata, we can do this efficiently. That includes things like reachability and safety objectives, which you can encode. For grammars and non-deterministic automata, it's now p-space hard because it's a two-player game. The same is true for temporal logics, like linear temporal logic. It's p-space equivalent, which is actually the complexity of this problem if you didn't have the randomness. If you're just trying to do ordinary reactive synthesis in a bounded window, that's already p-space hard. So at least the complexity of finding a randomized strategy is not any greater in this coarse-grained sense. Okay, that's what I wanted to say about the theory. Questions about that? Okay. So then I'll talk about one of the applications kind of inspired by this work to testing perception system. So I'm returning to this motivating example of a self-driving car. Imagine you have a camera on the front of the car and it's taking images like this. So obviously the system is operating in a very complex environment. There's a lot going on in this image. I'm going to call the state of the environment at every moment in time a scene. So this is not the actual input to the neural network or anything like that, not the raw pixels. This is a high-level configuration, like saying there are 12 cars, here are the XY coordinates for all the cars, and so forth. So collecting examples of those type of scenes, although very useful for training or testing, is difficult to do in real life because you can't just drive around and collect images. You have to have someone go in and label, here are all the cars, here are their coordinates, this kind of thing. So we would like to generate realistic scenes automatically for training or testing, because with a scene, you have the ground truths. You can test, is your network giving you the correct positions and things like this. what is difficult about this problem? Generating scenes randomly is easy. The difficulty is generating meaningful scenes because the scene space is very large and unstructured. So for a single car, you might have a bunch of different parameters. What type of car is it? Where is it? The orientation, color, and so forth. If you have a lot of cars, these add up. So if you, and furthermore, it's an unstructured space. If you just sampled randomly in that space, you'll get scenes that don't make sense. You'll get cars that are intersecting each other. Even if you block that, you'll get things that aren't realistic. You'll have cars facing backwards in a lane, this sort of thing. Realistic scenes have complex geometric constraints. For example, people tend to drive in lanes. They deviate in certain ways, but they usually drive in lanes, and so forth. Furthermore, you might be interested in particular types of scenes, like you want to know how well does my system handle an open manhole with traffic cones around it. So you don't want arbitrary scenes, you want ones of a particular type. So again, you can see this is kind of an instance of control improvisation. We have constraints, but we want to generate a random data set satisfying those constraints. But here the specifications are a little bit different. So let's look at that in a little more detail. We again have hard and soft constraints. So for example, like I said before, objects should not intersect. That's a hard constraint. For a soft constraint, you might want to say at least 20% of the images should be at night so that nighttime is adequately represented in our training set. However, you might also want to say something like this. The gap between cars in this traffic should follow this particular distribution, which maybe you've learned from data. That is a more sophisticated type of randomness requirement than what I talked about before. So what's the right way to encode that type of constraint? We argue that a probabilistic programming language is the most natural way to do that. So what we've done in this project is develop a language we call scenic for describing scenarios, essentially distributions over scenes. So as an example, these images we saw before are 4 different samples from a single scenic program. It's about 20 lines describing bumper-to-bumper traffic. So it says there are 3 lanes of traffic. Here's a distribution for the positions of the cars and this sort of thing. And even though this is a quite complicated scenario, it's only a short program in Scenic because Scenic has domain-specific, readable, concise syntax for talking about geometry. And what that enables us to do, in addition to describing kind of complicated scenarios, is also use specialized sampling techniques based on configuration spaces that you wouldn't be able to use in a generic probabilistic programming. But like ordinary PPLs, you can declaratively impose hard and soft constraints. So you can say, lay out the cars in this way, now require that these 2 cars are at least 10 meters apart. And the tool has to condition the distribution on that requirement. So there's a lot of related work we're drawing on in this project. From PPLs, for example, the semantics of Scenic are just that of an ordinary imperative PPL, so I won't talk about that at all. And such languages have been used as generative models of graphics, although not for test generation as far as we know. The main difference in Scenic is the domain specificity. There's also been work in computer graphics on scene synthesis from examples or from grammars, and in ML on data augmentation and generation. And the main benefit of Scenic over those is it gives you more control. You can say, this aspect of the scene should vary in this way, this part should remain fixed, and so forth. And we argue that a programming language is easier to use than, say, a shape grammar. So let me give you an actual example of what a Scenic program looks like. Say we want to write this kind of scenario, a badly parked car. So how would we do that? The first thing is Scenic doesn't have any knowledge built in about cars. It just knows about geometry because we, in fact, are using the language for things other than self-driving cars. So the first thing I'm going to do is import from this module everything specific to the case study we're doing, which is in this video game that people have used for self-driving car experiments before. So from that Scenic module that we define, I'm importing the notion of what a car is. So that's a class that defines priors on the various properties of the car. So for example, the position of a car, the prior says it can be uniformly over the roads, but not on the sidewalks, for example. I'm also bringing in the curve, which is a region. So that's a primitive data type in Scenic. Here, describing these red lines. So saying where the curves are in the simulated world. And the road direction is a vector field. That's another type in Scenic. Here, telling you at every point on the road, what is the nominal traffic direction. So the next, I'm going to create the ego car. That's the car on the left that we're going to render the image from. Notice I haven't said anything about where that car is and so forth. So we're using the priors defined in the class to specify all the properties of that object. Now I'm going to pick a parking spot for the other car. And the way I'm going to do that is I'm going to take the curve region, the red line, and pass it to this function visible, which restricts it to the part of that region that's visible from the ego. So here we're restricting it to just this black part. And then I'm saying, give me a point in that region or on that region, which means uniformly at random. So it might be that point, for example. And the oriented here is because we want to inherit this point to inherit kind of the local coordinate system of the curve. So it's oriented along the road at that point. Next, I'm going to pick an angle for this car to be parked at. I'm going to say uniformly between 10 to 20 degrees because we don't want it to be lined up. We want it to be somewhat off. It's badly parked. So this notation means uniform over that interval. We're picking an angle times 1 or -1 with equal probability. So to the left or right. And now I can start actually creating the car. So this syntax here is like the Smalltalk vector syntax. So it means a vector with -0.5 in the x and 0 in the y. So I'm taking the parking spot and I'm offsetting it by 0.5 meter to the left in the local coordinate system of spot. So it's not west, it's aligned with the road. And now I'm creating the car to the left of that. Now notice that in order to place the car to the left of that point, you need to know how wide the car is. So one nice thing that Scenic does is it keeps track of dependencies like that, and it figures out that in this case, I have to sample what the width of the car is, which could vary if you have various different types of cars, before computing the actual position of it. And now I'm saying the car should be facing that funny angle, not in the global coordinate system, but relative to the road direction. And again, notice the road direction doesn't define a unique direction. It's at every point on the road, it defines one. So Scenic tracks that this expression depends on the position and knows it has to sample the position of the car first before evaluating that expression. So this is a complete Scenic program. If we put this into our tool, it will sample scenes according to this distribution. If you then put those into the simulator, here in the video game, you get this type of image. Or you could also get out LiDAR data or whatever type of data the simulator supports. So here you see in every case, there's a car by the curb, but at a bit of a strange angle. Okay, so this is a simple example. You can do far more complicated ones, of course. Let me just mention a little bit about what we can do for specialized sampling in Scenic. The basic idea is to prune infeasible parts of the space by dilating polygons, similar to how robotic motion planning in low dimensions is done. So for example, in the previous Scenic program I didn't impose any constraints, but there are some built into the language, like that objects cannot intersect. Here, I'm using some Scenic syntax to impose new constraints, saying, for example, require that the distance to some taxi object is at most 5 meters, and that the relative heading of the taxi is between 15 and 45 degrees. So we want a taxi that's close to you, but it's turning or something. It's at a bit of a different angle. So here is a map of part of Berkeley that we use for some of our experiments. And what Scenic has done is prune almost all of the space away. So the red part is part of the space that's been pruned. The green is the only part left where Scenic can prove that outside of those green regions, it's not possible to satisfy those requirements. So we can just sample from inside those regions. And as you would expect, those regions are around intersections where the car could be at a different angle from you, whereas when you're on the straightaway. Okay, so what can you actually do with the language? So the most basic thing you can do is just explore the performance of your system under different conditions by generating specialized test sets. So just to show you an example that isn't a self-driving car, here's like a proof of concept we did, generating interesting cases for a robotic motion planner, where there's this Mars rover that can climb over rocks, but not these pipes, so the debris. And this scenario encodes kind of a bottleneck where it's trying to get to the flag, but the planner is sort of forced to consider crawling over these rocks between these two pipes. A more interesting thing you can do with Scenic is debugging a known failure. So here's an image we generated in one of our other experiments that for whatever reason the network misclassifies. It thinks this is 3 different cars. So now the question is why? Using Scenic, we can reconstruct this particular scene and now generalize it in different directions. We could say, leave the position of the car fixed, but change the model to see if maybe it's this racing stripe that's confusing it. Or add Gaussian noise to the position of the car. Or more interestingly, leave the position of the car in the frame fixed, but make the background totally different. And by iterating this a few times, we could actually converge on what the most significant kind of root cause of the misclassification was. In this case, unexpectedly, it turned out to be just distance to the camera. our training set didn't have enough images where the cars were quite close to the camera. The one last application that I'll go into a little more detail about is designing more effective training sets by emphasizing hard cases. So for object detection, one obvious difficult case is when one object partially occludes the other. So here we have a car that's partly blocking your view of another. So what these images are from is another scenic program we wrote that deliberately produces this type of scene where there's this partial occlusion. So we can generate a data set consisting of just these difficult images and use that for training. So what we did in this experiment is we took a data set from another group that used the same simulator. Basically, they let the cars drive around randomly in the simulated world, and they took screenshots periodically. So that data set, I'm going to call X matrix. If you train and test on that data, you get some numbers. The absolute numbers don't matter. The point is that if you evaluate it on our overlapping images, the precision is significantly worse here because it has trouble, the network has trouble localizing that car in the back. The recall is a lot better because these images only have 2 cars, whereas these can have an arbitrary number of cars. So then what we did is we trained a new network with the same number of images, same amount of computation time to do the training. But now we replaced 5% of the original training set with these overlapping images. Now, as you would expect, performance on the overlapping images goes way up. The crucial thing is that performance on the original distribution doesn't get worse. Actually, it surprised us, it somehow got a little bit better. So the point is that by emphasizing this particular hard case in the training set, adding in more examples, you can improve performance in that case without necessarily hurting performance in a typical case. And the language allows you to specify what those hard cases are and generate specialized sets of images or whatever data. Okay, so that's that application. Any questions about that?
Aren't you a bit worried that it might be a bit biased? Because as someone who has played that specific video game for thousands of hours, like there's a lot of physical problems that are not probably modeled.
That is true, of course. So here, I mean,
especially when you say that a lot of modelers use that as it's like ground truth.
So
it's kind of,
Right. So that, of course, is a particular issue. So one of the reasons we use this one is that it's been previously shown that this game's rendering is good enough and the simulated world is diverse enough that you can train purely on these type of images and get good performance on real images. So in particular, that's actually what that paper is doing, basically. They show if you train on like 200,000 images from this game, then you get better performance on Kitty, the real world data set, than you do by training on the much, much smaller real world training sets. But yes, that's an assumption of all of this work, that the simulated data has to be sufficient that you can make it make the system then perform well in real life. Of course, there's a lot of work on domain adaptation and things like that, which you could use there. But that's kind of an assumption underlying our work. Yeah.
So I sort of like the application domain and the motivation, but I'm just trying to think combinatorially. Like, what are the key algorithmic insights? For example, if I simply gave you a constraint satisfaction and asked to sample uniformly at random solutions to it, what are the key algorithmic intuitions that you have for that?
Oh, so yeah, so that's the model counting. The counting version of that is the model counting problem. Given Boolean formula, how many solutions does it have? There are a lot of algorithms for doing that, which are better than just doing, random sampling and hope you get an assignment, for example. So I've worked in the past on some of those algorithms. The particular one that I have worked on basically works by using a universal hash function. So the idea is you have just very briefly, we can talk more offline, but the general idea is you have the space of all possible assignments. The solutions are scattered in there somewhere, but you don't know where they are. If there were very few of them, like 12, you could enumerate all of them with a stat solver, and then it would say there are no more solutions. So the idea is you use a universal hash function, divide the space up into many, many buckets, so that each bucket has only very few solutions left in it, and each bucket is roughly of equal size. By using a universal hash function, you can ensure that that happens with high probability, even though you don't know how the solutions are distributed. Then you just enumerate everything in the bucket and extrapolate it to the whole space.
So is this kind of similar to the work that Carla Gomes did?
Yes, that's right. So that is, she and Bart Selman's group had some work on this a long time ago. Basically, the algorithms that I've worked on were from Moshe Vardy's group. His student, Kuldeep Neal, basically extended that idea to get stronger guarantees. So like Harlow's algorithm only gives you one direction, I think lower bounds, or is it upper bound? One of the two, upper bounds actually, I think. The other, you only have kind of a convergence and a limit sort of guarantee. And there have been refinements since then where you get double-sided bounds. That's the kind of algorithm I've worked on. Yeah. Okay, so let me just close here with some possible direction for future work. Whoops. So my work can be classified into kind of three different levels. Most of what I've worked on actually is kind of fundamental algorithms like model counting, the algorithm that I just described, and sampling. Control improvisation is one of those kind of fundamental algorithms you can use for a variety of different applications. On top of those, I've done work on languages and modeling, like scenic, for example. And then those enable a bunch of different applications to the design and analysis of different types of systems, like control improvisation is used for synthesis or for data generation that I just showed. Also, these other algorithms can be used for different forms of information flow, security analysis, things like this. And I think it's nice working on all of these levels in that the applications that we're interested in have really motivated development of new kind of fundamental theory and algorithms like this control improvisation problem. And then conversely, work on these types of fundamental algorithms has enabled new applications. So like my work on model counting enabled new types of information flow analysis that weren't really tractable. And in particular for control improvisation or algorithmic improvisation, because I think it's such a fundamentally new problem, there are rich possibilities to extend that work at all three of those levels. So I'll just illustrate a few. At the application level, I'll talk about intelligent test generation more broadly. The language level, new environment modeling formalisms, and then for the theory, a more generalized theory of control improvisation itself, and also theory for verifying systems with machine learning components. So at the application level, the idea is in Scenic, we're using a domain-specific language to guide a test generator. You can encode kind of your domain knowledge about what you think interesting tests are, and then have the computer generate many variations on those. Of course, what we'd like to do is to combine that with fully automated analysis if possible. So the human may not have all the information about where the bugs are. Of course, the human doesn't. So we would like to analyze the system and use that information as well to guide test generators. And I've done some work along these lines in a collaboration with JPL, this tool we call Contest, which combines a scenario description language like Scenic, but not for cyber-physical systems, for ordinary software, like a file system, with symbolic execution to refine that scenario and generate particular tests. And we had some success with this, for example, finding a number of bugs in the Mars 2020 rover flight software, which is obviously very heavily tested, very rigorously developed software. At the language level, an obvious extension of Scenic is to add dynamics. So everything I talked about was for generating a scene at one moment in time. But if you want to test like the, whoops. Okay, don't know what happened. If you want to test this Uber situation, so for example, this is the video I showed you before, we need dynamics. But notice the accident didn't happen in that one. So here what we're doing is we're using Scenic to generate variations on this accident. This was a quite straightforward usage where basically we were just varying the initial condition and now running the simulation from there. But what we'd like to do is add syntax into Scenic for talking about dynamics. So you could write scenarios like, there are 3 lanes of traffic, randomly between 2 to 5 seconds, someone cuts into your lane. And then test, can your AV controller handle that appropriately? So the hope there is that will allow us to write specifications and environments for whole systems, not just like a neural network, but the complete closed loop system. We've already done this in some experiments. An important part of doing that will be human modeling, of course, if you want to do simulations where there are other agents on the road or whatever system you have. And as I mentioned, you can use control improvisation to generate human-like behaviors. And besides our work on this, there's been some colleagues of ours at Caltech now have used control improvisation to generate a human-like lane change control, for example. But of course, for something like a self-driving car, the environment model, to be realistic, is going to have to be extremely complicated. So we're also interested in algorithms for learning these type of specifications from data. Finally, at the theory level, there are a couple of possible extensions that I think would be very useful. One is, as I described before, Scenic doesn't really fit into that theoretical framework because we have these more complicated kinds of randomness constraints, saying here's a particular distribution for part of the data. So a theory of control improvisation with distributional constraints would be useful for modeling that. Also, getting back to a question that Christina had asked a long time back, the randomness requirement that I stated before is a very simple one. But for something like the surveillance application, you might want to say something stronger, like bounding the mutual information between part of the trajectory and the future trajectory to rule out the possibility that certain statistics of the trajectory could be predictable in advance, for example. Finally, I talked a lot about using these kind of ideas to do testing in simulation, but an obvious problem with simulation-based testing, to the point you asked about, is do simulation results translate to reality? So of course there is work on domain adaptation and things like that, but even with all of that, it's still just testing in simulation. You don't have any kind of guarantees about what that means for reality. But I think there is a hope for a way to get stronger guarantees out of this type of simulation based on recent work on proving neural networks robust to perturbations of various kinds. So for example, what you could try to do is still do large-scale testing in simulation, but now prove that the system is robust to the gap between simulation and reality. For example, showing that the network doesn't depend on small pixel-level details of the rendering. So just to summarize, algorithmic improvisation is a framework for randomized synthesis with a bunch of applications, some that I didn't have time to get into in this talk, like fuzz testing and music improvisation, but also applications to safe autonomy, like controller synthesis and synthetic data generation. And the broader point, which I hope I have showed, is that formal methods can contribute in many ways, not just full formal verification, to the design, verification, and testing of autonomous systems. So I'd like to thank all my collaborators on these various projects and our funding agencies. And just to leave you with the big picture, I hope that there are, I think that there are good prospects that algorithmic improvisation and similar types of formal automated analysis could be used to develop a rigorous design process for these types of autonomous systems. Thank you. Yeah.
So have you considered, did you generate scenarios with motorcycles? Because motorcycles are the most dangerous things I usually take care of when I drive.
Right. So
that is really unexpected in real life, but I guess it's something you can also model.
Yeah, so you could absolutely do that. We haven't done that ourselves because basically in the experiments we've done, it was essentially just proofs of concept of showing the different things you can do with the language. We are talking to some car companies about testing some realistic controllers and things like that. And then of course, that would be another potential corner case, right? That would be good to specify with our language with some interesting positioning of motorcycles. Yeah, that's a great idea. We haven't done we just, for simplicity here, we only use cars. Yeah. Question?
So there is one piece of literature in the randomized algorithms community where, if you want to draw a random solution from a certain problem, then one way to do it is, let's say it's just a feasibility problem. One way to do it is to try and solve the problem which has the feasibility component as well as a random objective function. So, I mean, this sort of theory goes under the name of the isolating. Is there any connection that you see to this sort of?
Well, yeah, I mean, I think the algorithm that I described is working on, at a high level, on a similar kind of idea, right? Essentially, you take the original constraints and then you add this extra random, which eliminates most of the space, right? And then for sampling, I described the counting version, but sampling is exactly the same. You now just sample from a random bucket, essentially. So at a very high level, it's the same kind of intuition for why that should work. Now, we're not using those algorithms, for example, in scenic. There are various problems. For one thing, it's a continuous space, all kinds of stuff like that. But yes, I think we are interested actually in extending the formalism, which I talked about, which was for discrete alphabets, to continuous spaces. And then those, the specific techniques that you're talking about could be useful there. Yeah.
I have one more question. So I'm just curious about, suppose I gave you the problem of just finding, like on an undirected graph, I named 2 points, A and B, and I asked you to compute a random path between A and B,
right,
that is within W suboptimal times the shortest path.
Sure, sure.
How would you go about doing
So yeah, I mean, so if it's really just if the graph is small enough that you can encode it explicitly, so it's not like implicitly described or anything, then that would actually be, okay, I shouldn't say it would be efficient, but in theory, you can do that efficiently. We'd have to try it, but because you can represent all possible paths from A to B as an automaton, which just looks like the graph, essentially, right? Now you need to add in a bit of state to monitor the length, right, to make sure that it's within the bounds that you set. But once you've done that, assuming it doesn't blow up, the state space doesn't blow up too much, you just have a deterministic automaton then, and you can put it straight into these techniques, basically into our improvisation algorithm for automata. And that would be
the reason I bring this specific problem up is because, in the AI community, we have solved this very efficiently using what is called as focal search. Focal search is an extension of sort of A star search.
Okay, right.
So I think we can talk about
Yeah, I'd love to talk about it. Thanks.
Okay, so maybe an opportunity for someone else in the audience to ask a question. Speaker. Any more questions? Okay, if not, thank you, Daniel.
All right. Thank you.
I was expecting to see more neural networks.